So friends, we have arrived at our second algorithm, which is logistic regression. It is part of supervised machine learning, and we are going to understand how classification can be done by the use of logistic regression. We'll be using a specific case of binary classification here. So let's get on with it. Friends, let's first understand how the mathematics of logistic regression works. In linear regression, friends, we understood that a certain dependent variable y is equated with multiple or single independent variables like x1, x2, x3, x4, etc. etc. Now we add various weightages to them, for example a1, a2, a3, a4, right? And we create an equation like this. This equation does not give us exactly accurate results, but it predicts results in a reasonably good way if the equation is done if the weightages are calculated properly, right? And this gives us the y predicted or the y hat. Now, in logistic regression, there is a critical difference from linear regression. What is that? Let's understand, friends. Let's say we were doing an equation on salary predictions, right? Now the salary could be 10,000, it could be 10 lakhs, it could be 10 million, it could be 5,000, it could be 50,000, any such numbers, right? Depending on whatever the parameters are. There's a range of variables that are possible, right? In case of logistic regression, this is not the case, friends. In case of logistic regression, let's say if it's a binary logistic regression, this equation has to give us either 1 or 0. That is what creates the main difference, and the mathematics changes from this point, friends. Let's look at the data that we are going to use for our coding. So this is the data related to social marketing ads, and our dependent variable is whether a person clicked on ad or not, right? Clicked on ad or not. This is our y. And to ascertain that or to predict that, we have been given certain features. That is, we have been given daily time spent on site. This we can say is x1. Age, we can say x2. Income, x3. Daily internet usage, x4. Gender, x5. Right? These are the informations which are used for predicting whether a person is going to click on an ad or not. Okay, friends? Now, our responsibility is basically to create an equation out of x1, x2, x3, x4 and x5 to ascertain the right value of y, or ascertain to a great extent the value of y rightly. So how do we do that, friends? Now when the person has already clicked on ad or already rejected to click on the ad, the event is absolute. It is either 1 or 0, right? But when it is a futuristic event or when it is an unknown event, these parameters x1, x2, x3, x4 and x5 basically give us a probabilistic idea of what the eventual outcome can be. So for example, it can be 0.8 or it can be 0.2 or it can be 0.1 or it can be 0.9. These are probabilistic numbers that we can have. Perfect numbers we cannot have in an unknown or a futuristic scenario. So these are the numbers we have to be satisfied with. Now how can these variables and this y give us these values? And it has to be within a range of 0 to 1. The range has to be 0 to 1. So for that, we change the equation a little bit. We change the definition of y a little bit. Okay, it's not similar to linear regression. What is that? Let us look at it. Here, y is the probability of clicking on the ad. Therefore, the probability of not clicking on the ad comes to be 1 minus y. So this will be 1 minus y, which is probability of not clicking. Now friends, our objective is this equation has to remain within 0 and 1. This is achieved in a very unique way. What we do is, we take the ratio of y and 1 minus y, we take the natural log of it, and this is what we equate to the features with different weights. So this is equal to a1x1, a2x2, a3x3 and a4x4. Remember, here gender is there. We are not going to use any dummy variables because there are only two classifications of it, 0 and 1. Here 1 is denoting male and 0 is denoting female. So we can keep it that way. We do not have to add any dummy variables. Otherwise, the only thing that we had to do in case of a categorical data, if the categories were more than 2, we had to introduce something called dummy variable. We will look at it later definitely. Now we come back to this equation. So this equation remains within the diameters of 0 and 1. It does not cross 0 to become negative, and it does not go beyond 1. How? Let us look at that. Let's say, friends, this entire equation a1x1, a2x2, a3x3, a4x4, this is equal to z. Okay, we are denoting this entire expression as z. This implies that natural log of y divided by 1 minus y is equal to z. This implies y by 1 minus y is equal to e to the power z. Right, friends? Now we rearrange the equation to get the expression for y. Now this becomes 1 minus y by y is equal to e to the power minus z, because if we invert this, this also inverts and becomes 1 by e to the power z, which actually means e to the power minus z. Now we rearrange it further. What we do is 1 minus y is equal to e to the power minus z plus 1. From this evidently implies this, and y is equal to 1 by 1 plus e to the power minus z. Now this is the magic that actually enables us to keep the value within 0 and 1. Now how? Let us see through a demonstration. Now friends, before we do the demonstration, let us contemplate what would have happened had we not done all this circus. Let's say we were bent that we will use the same equation, we will not go for any other equation and try to do logistics. Let's see what would have happened, or try to do classification. Let's see what would have happened. Y is equal to a1x1 plus a2x2 plus a3x3 plus a4x4. Now let us draw a graph and plot the probabilistic numbers. Let's say the horizontal axis denotes the features and the vertical axis denotes the y. Now here there is 1 and this point of intersection is 0, right? Now let's say when the feature values are at a certain point, let's say when the feature is here, feature set is here, the value of y is here, right? So there is not a problem here, friends. It's within 1 and within 0, there is not a problem. Also, let's say the point is here. Now this means, let's say y goes till here. Here also there is not a problem. Maybe it is touching very close to 1. It is not crossing it. But what happens? What happens if the feature set is here? It might be possible that y comes somewhere here. Isn't it possible? Or let's say if the feature set is here, what would happen? It might just happen that y comes somewhere here. So this is well below 0, right? This is well above 1 because we are using our so-called linear regression format. This is the format we are using. It cannot sustain the numbers within 0 and 1, which is a primary necessity for us to do this binary calculation, friends. That is why we have to make it within 0 and 1, and we do it through this equation. Y is equal to 1 by 1 plus e to the power minus z. This expression has been compressed and said this is z. We have said this is z. Okay. Now this function is called the sigmoid function. There is a reason for it. Let's see how and what is the reason. Let's say there is a scenario 1 where let's say there is a scenario 1 where z is very, very high. Right? Z is a very high number. Then what happens, friends? What happens, friends, is basically this equation. In this equation, e to the power minus z, this number becomes very, very low. If this number becomes very, very low or close to 0, what happens is the value of y comes very close to 1. Because you can say this number is almost 0, right? So therefore 1 by 1 is very close to 1. Therefore y remains within 1. But it never touches exactly 0. It becomes very low. So therefore it comes close to 1 but never reaches 1. Let's take another scenario, scenario 2. Z in this case becomes very, very low, or a very high negative number. Z is much less than 0. In this case, Z was much greater than 0. Now we have taken a case where Z is much less than 0. Here what happens, friends, is y is equal to 1 by 1 plus e to the power minus z. This minus z being negative expression and z being itself another negative expression. So z minus of a negative number is equal to a positive number, and because this is the magnitude of this number is very high, so what happens is this power of e becomes very high, and power of e becomes very high means this entire expression becomes very, very high. So basically this expression is converted into y is equal to 1 by a huge number. Now 1 by a huge number is actually something very close to 0. It does not become exactly 0, but it comes close to 0, but remains within the boundaries of 0. So whether z goes far beyond 0, that is on the positive side, if it becomes a far positive number, high positive number, then also y remains within 1. When it becomes a very, very huge negative number, then it also remains within 0. So whatever may be the value of z, y oscillates between 0 and 1. It never breaches the boundaries of 0 and 1. The graph basically looks like this. This is the vertical axis is the y, and this is the feature axis, that is the horizontal axis. I denote it by capital X. Let's say here there is 1 and here it is 0. The sigmoid function graph moves something like this. When z becomes very negative, it remains within 0. And when it becomes highly positive, it remains within 1. So the entire story is it remains within 1 and 0. So this is the magic of the sigmoid function, which enables us to do classification through logistic regression. Now friends, we will move into the practical section where we will code it and see what transpires. Now let us import a few things, friends. We will need to draw graphs, we will need to create data frames, and we will need to work with numbers. So for that we import 3 modules. To create data frames, friends, we import pandas. Import pandas as PD. To play with numbers, we need something called numpy. Import numpy as NP. And to create graphs, we'll install 2 things. Import matplotlib.pyplot as PLT and import Seaborn as SNS. Now we have imported the right modules. Now what we do, friends, sorry, there is an error, it's matplotlib. Now what we do is we call the data. df is equal to pd.read, it's a CSV file, so read CSV within colons, within quotes, advertising. So advertising with an S, CSV. Now let us see how the data looks. Yes friends, we have segregated the data, or we have called the data. Now what we have to do, friends, we have to isolate the features from the outcome, or from the label, or from the Y. So we have to separate out the features from the prediction outcome. First we segregate the features. For that we write X. X is equal to df.iloc. We need all the rows, so for that we write a colon, and we need all the columns except the last one. So for that we write 0 till 1, 2, 3, 4, 5. 0 till 5. Let's see. Yes, all the columns have been isolated. Now we create the Y variable, which is the dependent variable. For this we need only the last column, df.iloc. We need all the rows. We can just put a colon and it will select all the rows, and we need only the last column, so we write 5:6. We have the last column. Now friends, we have divided X and Y, but we do not have a data separated for training and a data separated for testing. So we need to do that. For that, what do? We create a training data set and a testing data set, both for X and Y. And for that, we import something called train test split from sklearn dot model selection import train test split. Now we want to have 25% of data as test data and train the module or the logistic model on 75% of the data. How do we do that? X train, comma X test, comma Y train, comma Y test is equal to train test split. We split it by using X and Y. Test size is 25% or 0.25, and we add something called a random state and put say 42 here. So test size we already understand, it's 25% of the data we want as test. Random state, what does that mean? Basically friends, random state we use so that we have identical splits no matter how many times we split the data. For example, this is now we execute it. Shift enter, we have executed it. Now if we do it separately for 10 times with the same random state and same test size, we will have identical X trains, X tests, Y train, Y tests. It will never so happen that in some iteration some data went into Y train and in that data in some other iteration entered Y test. This thing will never happen. The separation or the splitting will be identical even if you do it for 100 times. If you keep the test size and random state identical, the splitting will be identical. Now let's check what has happened to our data. X train, see, there were total 1000 rows. In X train now there are 750 rows and 5 columns. What about Y train? Obviously 750 rows and 1 column. X test, it should be 250 rows and 5 columns. Yes. Y test, 250 rows and 1 column. It should be, right? And here it is. So we have split the data successfully to our desired ratios. So friends, splitting is all good. We have split the data and the data is ready for the module or the model fitting. But before that, we want to visualize the data a little bit, have some interesting observations come out of it. So how does the data behave? Let's see. The first thing that we want to see is what is the age distribution of the data. So for that, what we do is we do sns.histplot df age. Now you can see here friends, the modal age or the highest frequency age is around 30. So the database here signifies that the maximum amount of age group in this data set is around 30. Now let us try to understand how this age group and earnings are distributed. What I mean is, how does age relate to earnings here? Let's see that. We will do it through something called join plot. sns.joinplot x is equal to df age, y is equal to df income, and the data we are going to use is obviously df, data frame. So friends, as you can see, this is the way income and age are related. Around 30, you can see the maximum density of income is around 60 to 70,000. And as we move towards higher numbers, the numbers get more scattered and more, it can be very low also, very high also, really doesn't give a definition. But around 30, it is around 60 to 70,000 in a very large numbers. Very less number of people are lower in salaries. Now, one more interesting observation we can make is, how does internet time spent relate to age? Let us try to understand that. So age and time spent on the internet, right? Daily time spent on the internet. This is our Y. Data is DF. Let's change the color a little bit. It's becoming too blue. Color is equal to red. Let's change the kind also to KDE. Let's see. Yep, we have the chart. So again, time spent is pronounced somewhere around this spot, 30 age. Then we make our next observation. Let us do first an overall pair plot, friends. So SNS dot pair plot DF. So friends, you can see there is some relation between age and daily internet usage. There is some relation between age and time spent on the internet, age and income. Like this, we can observe a few relations, a little bit of lopsidedness in terms of data densities. Now we move on to our next observation, friends. So friends, now we try to understand what is the relationship between the clicking on ads and the age. So we'll try to understand it through something called violin plot. SNS dot violin plot. Here the syntax is very much like the joint plot, but the only thing is the categorical number has to be, or the categorical variant has to be on the horizontal axis. So we say X is equal to DF clicked on ad Y is equal to DF age and data obviously is DF. Now we draw the violin plot. Shift enter. Here we have it, friends. So you can see those who have clicked on ad are majorly around 40, and those who have not clicked on ad are majorly around 30. This is what this violin plot shows. We can draw another violin plot, friends, just to see income and clicked on ads. So we can write here income instead of age. Income. Now those who have clicked on ads, surprisingly, you can see here, are majorly around 50,000, earnings of 50,000. And those who have not clicked on this ad are earning around 60 to 70,000. The maximum frequency of that is around maximum 60 to 70,000. From sklearn dot linear model import import logistic regression. Now we are going to fit the data. Let's see how to do that. Log reg is equal to logistic regression. We have called it. Now we are going to use it for the fitment. Log reg dot fit. We are going to fit it with X train and Y train. X train, Y train. The model is ready. Now we are going to predict, friends. So log reg dot predict. We'll be predicting the y values using the x test values, right? To get the y hat, we have to use the x test, right? So we do that, and this is what we get. So this is y hat or y pred. Y hat, let's say. Now, how do we decipher what is the performance level of this prediction? We need something called confusion matrix. Obviously, we'll get into the details of it, but first, let us call the confusion matrix module from sklearn. I think it's in metrics. sklearn.metrics import confusion matrix. Yes, it is there. One more thing we will need is something called classification report. It basically ascertains the performance of the confusion matrix. Classification report. Okay. Now let's use the confusion matrix first. Confusion matrix is equal to confusion matrix y test, and we are going to compare y test with y hat. Now let us see what the matrix looks like. Okay, 117, 25, 3, 105. Now what do these numbers mean? We have to go to the blackboard and see what this means. So friends, the confusion matrix gave us these four numbers in this format. Now, what do they mean? That is the main question. And how do we ascertain the performance of the logistic regression through these numbers? Let us see that. So friends, here, this vertical axis of this matrix denotes the actual values, that is the y test values, and the horizontal axis denotes the predicted values, that is the y hat values. And this column, this first column, denotes prediction is equal to 0. This one, the second column, denotes prediction is equal to 1. Here, the actual is equal to 0. The first row, that is. And the second row indicates actual is equal to 1. Now, actually it was 0 and prediction was also 0. This is that box, right? This is that box. This box we call true negative. We call this true negative. The second box, this box, the actual was 0, but prediction said it's positive. So we call it false positive. Because the actual was negative, prediction said it's positive. Actual said it's 0, prediction said it's 1. So this is false positive. Now we come to the third box, 105 1. Here the prediction was 1, actual was also 1. This is the box of true positive. Prediction was 1, actual was also 1. So we call this box a box of true positive. The fourth one, actual was 1, prediction said it's 0. So we call it false negative. That is, the prediction said it's negative, but that prediction was false. So it's a false negative. Now there are certain parameters with which the performance of a confusion matrix can be judged. Let us first know about those parameters. The first parameter is accuracy. This is measured by total correct predictions by total number of data points. So, total correct predictions divided by total number of data points, which means total correct predictions means true negative and true positive. So TP plus TN, and total data points means all these four boxes taken together. So TP plus TN plus FP plus FN. So this is equal to TP is 105, TN true negative is 117, 105, 117 plus false positive FP is 3 plus false negative FN is 25. So this comes to 222 divided by 222 plus 3 plus 25. So 222 plus 28, this comes to 250. Now if we take percentage, this comes to 88.8%. This is the accuracy of the logistic regression that we have done. The next metric is precision. This is the ratio of correct positive predictions by total positive predictions. Correct positive predictions divided by total positive predictions. This is equal to the true positives divided by the true positives and also the false positives, because they are also positive predictions, but only thing is they are false. So this comes to be, in this case, FP is 3, TP is 105. So 105 by 105 plus 3. This is equal to 105 by 108. The percentage comes to be 97.22%. So very high precision is achieved here, friends. Now the second thing that we want is recall. So friends, recall is defined as correct positive predictions divided by actual number of positive predictions. This is nothing but, friends, TP by TP plus FN, false negatives, because false negatives were actually positive, but the predictor called that it will be negative. So this is equal to 105 by 105 plus, if I'm not wrong, 25. Let's see. Yes, 25. So this comes to be 105 by 130. 105 by 130. Percentage wise, 105 divided by 130. 80.77%. 77%. Now friends, there is a catch between precision and recall. Let's explore what that is. In some cases, the parameter false negative becomes highly important. For example, in disease detection, a false negative can be very costly. So in case a model is using disease detection, that whether some disease has happened or not happened, recall is the more important parameter than precision. Any day we will choose the recall parameter to be high. Precision we will not give that much importance. Okay, this is an example of prioritizing between recall and precision. Another example where precision can be more important is, let's say, spam detector in a CEO's mail ID. So CEO's mail ID, we are applying a spam detector on it. Here, friends, the false positive is tremendously important. Let's say a very important mail which is not a spam is predicted as spam. That mail will get deleted. Therefore, in case of this kind of an algorithm, precision becomes much more important than recall. Now, there can be a case where we do not want to choose between precision and recall. There we use something called F1 score. Now we will measure the F1 score. Fourth parameter we'll write here only. Fourth parameter, F1 score. This is used in the case where recall or precision neither take precedence. So this is basically the harmonic mean of recall and precision. So how do we calculate this? This is equal to 2 by 1 by precision plus 1 by recall, which means this is equal to 2 precision multiplied by recall divided by recall plus precision. In our case, the value will come to be, so the numerator is coming to be 1.57. We have used decimal versions of percentages, friends. Below also will do that. 0.9722 plus 0.8077. This is 1.7799, and this comes to be 88.2%. So this is basically the performance of our confusion matrix. Now we have done it manually. What if we want to do it in Python? Let's see, friends. Herein comes the application of classification report. Print classification report, y test, y hat, that is y predicted, and we press shift enter. Now you can see, friends, precision, recall, F1 score, everything is here. Here you can see there are two sets of precisions and recalls. The reason being, here we have chosen 1 as true, 1 as positive and 0 as negative. The reverse will happen if we choose 0 as positive and 1 as negative. So both the numbers have been shown here. So friends, that's about it for our logistic regression. In the next class, what we'll do is we'll go deeper into the linear and logistic regressions. One thing is we haven't learned the cost function aspect. So we will have to learn how these algorithms actually are working under the hood. This implies that we have to learn something called the cost function. What it is and how it works, we'll see in the next class. For now, bye bye and happy practicing these